Well, good morning, ladies and gentlemen. My name is Squadron Leader Evan Smith. I'm a part-time PhD student with the School of Engineering and Information Technology. My supervisor for this research is Associate Professor Andrew Neely. My topic is the effect of gas turbine design and integration on shaft thermal bow and the Newkirk effect. So I appreciate that there's a range of different types of expertise here, so I'm going to try and explain my research to you in some simple terms and avoid using excessive engineering jargon. Put simply, we're talking about gas turbine engines or jet engines on aircraft. For those of you who are unfamiliar with jet engines, they run at elevated temperatures. The compressor section, which is the area of interest, which is the area denoted there by 2 and 3 on the upper surface, runs in excess of 500 degrees Celsius on high-performance engines. After you shut them down, they obviously begin to cool. And for those of you who have a cup of coffee with you, you'll notice that the steam rising from your cup of coffee is going up because hot air rises. Same thing happens in a gas turbine. As you begin to cool the gas turbine, the hot air rises to the top of the engine and pools in certain parts of the engine, not only externally in the flow path, but also inside the compressor drum, which is a hollow metal shaft. So as the hot air rises and pools in certain parts of the engine, then you have metal components in the shaft which are exposed to higher temperatures than others. As they cool, you start to see an onset of a thermal difference or a temperature difference across the metal components. And because of thermal expansion, when a metal component gets hot, it expands. As the component cools asymmetrically, you actually get a differential expansion in the shaft, which results in a bending of the shaft, which we call shaft thermal bow. So what you effectively see is the compressor section of the shaft is actually bending ever so slightly. That's fine while the engine is stagnant. But as soon as you start the engine, the very tight tolerance seals in the engine will begin to rub. And if you've got enough bow and those shaft seals begin to rub, you can generate more heat. And in a phenomenon called the Newkirk effect, you can actually generate more bowing, which can actually lead to severe damage to the engine. So that the image there labelled engine failure is a helicopter engine failure that occurred in the Australian Defence Force from this very phenomena, whereby over several iterations of this damage mechanism, eventually the blades failed in flight and resulted in unrecoverable in-flight shutdown. Obviously a dangerous scenario because you want to have you want to have both your engines running in a dual-engine helicopter, and obviously in a single-engine aircraft, failure of an engine is catastrophic. But also very expensive. Repair of this engine was in excess of $1 million. So my research aims are to improve an understanding of this mechanism, both the engine design aspects and also the integration aspects, how you install an engine into an aircraft, to understand how they affect that thermal bow and subsequently how they can lead to the Newkirk effect. Specifically, I'm looking at certain aspects of the effect being the onset time, the time taken after shutdown to reach a certain level of bowed condition, the severity or how bad the bow actually gets after a given period of time, the duration, so the period of time over which the engine is actually susceptible to that bowed condition, and the location, so where on the shaft does the peak bow actually occur. The method that I'm using, basically I'm using very simplified engineering models, three-dimensional models in a computational fluid dynamics program, which is an engineering program, which models the heat transfer from the component. Using that, I'm actually able to model the heat transfer from the solid components into the air and model the escape of the heat through the buoyant plume. And I can export the body temperatures out to another engineering program called a finite element analysis tool, which allows me to measure the structural deformation or the bending of the shaft at any given period of time. The aim then is to slowly increase the complexity of the model so that with each increased design element, I can measure the effect that that design element has had on those various aspects of the thermal bow condition that I was talking about before. So that you can visualize what I'm talking about, I have some images here. On the left-hand side, you can see 3 of my models that I've used so far. On the top, we've got the baseline model, which is a very simplified shaft and case arrangement, which effectively models the compressor shaft and the enclosure of the compressor case. And you can see very clearly there that there's a buoyant escape of heat in the model. Similarly, going down the left-hand side of the page, you can see my second model, which is effectively an enclosure model representative of the type of enclosure an engine would see in a fast jet or a buried installation. And you can see very clearly there that the buoyant plume has been trapped at the upper surface of the model. And the third model on the bottom is a representative of a helicopter type installation with a flow restriction on the inlet, representative of a filter, and an upturned exhaust representative of an infrared suppression system. And you can clearly see there that the three models drastically affect the behaviour of the buoyant plume. In the middle, on the upper surface, you can see an export of the body temperatures. That enables you to visualise what I was talking about with the thermal difference that becomes apparent after a period of time. The red upper surface of the shaft is hotter than the bluer lower surfaces of the shaft. If you go across the page to the top right, you'll see a very slight bowed condition from the shaft. And we're talking about half a millimetre or less, or 0.05 millimetres in fact in some cases. And it might not sound like a lot, but in modern gas turbine engines, the seal clearances in Labyrinth seals, for example, are in the order of less than a millimetre. The tighter you can get a seal clearance, the higher the performance of the engine. So it doesn't actually take much of a bending condition or a bow condition in the shaft to consume that seal clearance and result in rubbing on startup. The larger graph that you can see there is an export plot of the bow, basically a measure of the bow in millimetres, from 0 minutes after shutdown out to 90 minutes after shutdown. You can see that after a period of time, the bow reaches a peak condition and then begins to gradually degrade. For a given gas turbine design, if you were able to, or if you knew what the critical bow was for the onset of the Newkirk effect, or basically if you knew how much seal clearance you had before you would see rubbing, you can quickly and easily plot a line across to see how quickly it reaches that critical bow condition and also how long it remains above that bow condition. We call that the danger period. In terms of what that means physically for an aircraft or a military operator, for example, if you wanted to restart your engine in that period of time, you would have to do something about it to mitigate the damage mechanism. In real life, we see on certain helicopter fleets, if you want to start, say, from 22 minutes onwards, you would need to ventilate the engine or crank the engine over using the starter motors. And while that's quite effective at reducing the bow condition, it does mean that the aircraft can't take off for that period of time. If you're talking about a high-threat military environment, then the aircraft is effectively grounded for that period of time. And if they're under attack, they have a choice of either waiting and exposing themselves to greater risk, or they can bypass the mechanism and take off and risk damaging the engine. So the goal is to understand how all of those various design elements, and not only these ones that I've looked at here, which are installation type design mechanisms, but also internal design mechanisms to the engine, how they affect that onset time or the time to reach the critical bow condition, and how long it lasts and how bad it actually gets over time. Initial results show, looking at the inlet and exhaust geometry analogues, that they do actually have quite a significant effect. The blue line there is the baseline model, effectively no inlet or exhaust condition. And you can see that the bow is a lot smaller than the other two cases and much more gradual. Whereas the helicopter, primarily driven by the upturned exhaust, which draws air through the engine and cools parts of it faster than others, sees a much greater bending condition, a much greater severity of the bending condition. It reaches it faster, but it also cools, degrades more quickly. Whereas the buried installation, which is kind of like what you would see inside a jet aircraft or a fighter aircraft, still reaches a much more severe bow condition than the baseline model, but lasts a lot longer, which is also not ideal. Initial results have also shown that the presence of blades in the flow will have a significant effect, and the shaft's initial temperature, or the temperature of the engine after it's shut down, also obviously has a significant effect on how bad the bow is. Future work is going to take these simplified models and build in more complexity to step them up towards the real model, a realistic representation of a gas turbine engine. And that includes incorporating the other parts of the engine that haven't currently been modelled, including the turbine, combustor section, rotor and stator blades, or the blades that actually move the flow through the air, rising and falling line annulus geometries, non-uniform initial shaft temperatures, and also changes in ambient conditions. Are there any questions?
So I have a question.
Yes.
So it's been a long time since I've messed around with finite element analysis, but
Yep.
have you compared your results to experiment In other words, have you been able to verify the models are actually showing you what's really happening?
The closest thing I've done to any sort of validation at this point is to do with the heat transfer validation. So I've taken simplified flat plate models and verified that the heat transfer rate and the cooling rate of those flat plate models is approximately correct. I've seen good validation from those cases. I haven't done any physical validation in terms of experimental work, but we have seen, since this has actually happened in real life, and I have had some exposure to that in my work, I've seen that the type of bowing that you get is in this rough order of magnitude. And furthermore, the fact that we're seeing bowing in the order of the magnitude of the labyrinth seal gives me some confidence that it's an appropriate level of deformation. If I was seeing huge deformations, for example, that were well and truly unrealistic in terms of gas turbine design, that would probably prompt me to question the results a bit more.
Thank you.
Thanks.